Today, our picture of the universe changed. In a groundbreaking paper published in the journal Nature, an international team of astrophysicists led by Astraveo's very own Joseph Farah has used a global network of telescopes to make an astonishing discovery about the way stars die. Across the universe, 1 billion light-years away, a supernova exploded, and then began to do something never seen before. Something that had astronomers around the world scrambling for answers. Unraveling this mystery would lead them to an astounding explanation, solving a major open question of astrophysics, unveiling the birth of one of the most exotic objects in the universe, and ultimately providing a new way to test our deepest, most fundamental theories of reality. Join us as we investigate the extreme physics that beats at the heart of a dying star, right now on Astraveo. When a massive star dies, its core collapses in a violent explosion known as a supernova. This explosion is so bright and so spectacular that it will often outshine the entire galaxy in which it resides for weeks at a time. Seeing as the Big Bang only produced hydrogen, helium, and lithium, supernovae are among the most important drivers of galactic evolution and chemical enrichment of their local environments, forging and dispersing most of the heavy elements into the universe. These elements include the oxygen in your lungs, the iron in your blood, and even the silicon and copper in your telephone's silicon chips. Supernovae are also so bright that they can be seen halfway across the universe. They light up their immediate environment, giving us a view like an X-ray into their host galaxies and allowing us to learn about the chemical composition and structure of the cosmos at vast distances from the Earth. Some supernovae are so consistent and predictable that we use them as standard candles, measuring the distance between faraway galaxies and the accelerating expansion of the universe. As astronomers, we mostly thought that we had a handle on supernovae, how they work, and why they are so explosive. There are two primary types of supernova. In the first, a red supergiant star dumps mass onto a small white dwarf until it reaches its limit and explodes in a fiery outburst. In the second type, a massive star runs out of its nuclear fuel and collapses under the weight of its own gravity. These two mechanisms can explain the overall behaviour and brightnesses of almost all the supernovae that we see in the night sky. And it's a good thing too. It's pretty hard to find ways for a single star to generate enough energy to outshine an entire galaxy. In the last 20 years, however, astronomers have discovered a new type of supernova that is 10 to 100 times brighter than regular supernovae. These so-called superluminous supernovae take the most extreme events in the universe and punch that dial up to an 11. This shouldn't really be possible, so the question astronomers have been asking themselves is, how do they shine so brightly? It's not just a mystery, it's actually a big problem. Superluminous supernovae can be seen orders of magnitudes farther away than regular supernovae, meaning we can get glimpses of the cosmos at even more distant, which means farther back in time. Without an understanding of how they work, we cannot use them as probes of the physical conditions in the early universe as effectively as we would like. And it gets worse. Not only are these supernovae extremely bright, they are also extremely bumpy. Unlike most supernovae, which evolve smoothly in time, a majority of superluminous supernovae have strange bumps and wiggles and modulations in their time-dependent light curves that cannot easily be explained. These temporary power surges defy expectations and point to even more exotic, hidden physics inside the expanding supernova. For almost 2 decades, theoreticians have been trying to solve the puzzle of superluminous supernovae, and we do now have a few ideas. The first main idea is that the shockwave from the supernova is slamming into dense clouds of gas and dust around the star, its so-called circumstellar material. Before the star collapsed, it cast off layers of its outer envelope in a series of shells. Later, when the supernova shockwave runs into that material, it makes it glow extremely brightly. The random nature of the mass loss mechanism that caused its circumstellar material can potentially explain the uneven, bumpy evolution of the superluminous supernova light curves that we see. The second school of thought is that the nuclear death of the star leads to the birth of something far more extreme. When the progenitor star collapses, it squeezes its core with such force that electrons and protons merge together into neutrons, creating a neutron star, an object with the mass of the Sun compressed into the size of a city on Earth. This neutron star inherits and amplifies the magnetic field and angular momentum of the dying star, spinning thousands of times a second, generating and deploying a ferocious magnetic field hundreds of trillions of times more powerful than that of the Earth. The neutron star has become a magnetar. Powers the supernova from within like a huge battery, easily explaining the overbrightness and evolution of the supernova. Unfortunately, the magnetar injects its power into the supernova smoothly, and this mechanism by itself cannot explain all of the supernova properties, especially its bumpy and wiggly light curve. Both these ideas have their pros and cons, but the real issue is that we have no way to test either of them. We can fit theoretical models to the limited telescope data available, but studies so far have found no conclusive evidence strongly favouring either scenario, which means we are still in the dark on superluminous supernovae. Thanks to an exciting new discovery, we may have an answer to the mystery of superluminous supernovae, what they are and how they work. At just over 1 billion light-years away from the Milky Way galaxy, a star died in an explosion astronomers have labelled SN 2024 AF-AV. Around the world, astronomers triggered telescope observations watching the explosion from both ground and space, in every band of light, from the long wavelength infrared up to the short wavelength X-ray regions of the electromagnetic spectrum. At Las Cumbres Observatory, we triggered our global network of telescopes to begin taking telescope data of the supernova, once per day. The light curve of the supernova rose smoothly for about 40 days up to its superluminous peak, over 100 times brighter than an ordinary supernova. Post-peak, it began to execute an incredibly violent series of modulations observed in its multi-wavelength light curves. If we look at the modulations alone, subtracting off the bulk evolution of the light curve, we see something never before seen in any other supernova. A light curve that looks like a sine wave, and with a frequency increasing with time in a signal known as a chirp. It is hard to truly appreciate how unusual this is. Over the entirety of human history, we astronomers have only discovered maybe 15,000 supernovae in total. Of these, only a small handful have had anything resembling a clearly sinusoidal light curve, and these are usually noisy and are very unclear. And even of this small handful, not one has had a chirp. This truly is a baffling and astonishing discovery, evidence of something genuinely completely new in the cosmos. So, as scientists, how do we begin to explain something that has never been seen before? Of course, we start with what we already know. We can try to explain the bumps in the multi-wavelength light curves with circumstellar material interaction, where the supernova slams into the material around the star. But light curve bumps due to circumstellar material tend to be random and irregular. There's no simple mechanism that we know of for them to produce a perfect sinusoid in the underlying light curve signature. So we need to try an option 2, of course, a magnetar. If we place a magnetar spinning once every 4 milliseconds and with a magnetic field strength of 10 to the power 14 Gauss, that's 100,000 billion Gauss, in the center of our supernova, we find that we actually can reproduce the overall shape of this supernova's light curve. However, as before, we are unable to reproduce the bumps in its light curve. Worse still, there is no known modification to the magnetar model that can produce a sinusoid with a decaying period, only an increasing one. In terms of supernova 2024 AF-AV, we were well past the limit of employing existing theoretical ideas which could help us explain this cosmic explosion. So it's time to get creative and think outside of the box. So that's when we had this wild idea. What if the magnetar is not alone? According to a new mechanism proposed by Joseph's research team in a recently published Nature paper, the magnetar first formed in the heart of the dying star. Subsequently, the supernova occurs, ejecting most of the stellar carcass into space at tens of millions of miles per hour. Most of the stellar materials, but not all. A tiny fraction of the dead star fails to be ejected and is recaptured by the nascent magnetar and forms a tilted accretion disk. As the magnetar spins hundreds of times per second, it twists the fabric of space-time with it due to its immensely powerful gravity. This effect, known as frame dragging or the lens-thirring effect, causes the accretion disk to begin precessing around the magnetar, just like a spinning top, which causes the disk to change its orientation with time, sometimes blocking the magnetar from our view, sometimes showing it. This mechanism produces a sinusoidal wiggle in the multi-wavelength light curves observed by our telescopes. As the accretion disk continues to fall toward the magnetar under its intense gravitational pull, it shrinks. The precession frequency increases and the modulations happen faster and faster. This model perfectly explains the previously unexplainable light curves, reproducing each modulation we observe precisely. And best of all, the physical properties of the magnetar required to produce precisely these bumps in the light curves have the exact same properties as the magnetar needed to produce the overall evolution of the supernova itself. This represents, for the very first time, a smoking gun confirmation of the magnetar model for superluminous supernovae, solving the mystery of why they are so bright. However, confirming that infant magnetars power superluminous supernovae is not the only reason that this discovery is so intriguing. Lens-thirring precession is an effect found only in Einstein's theory of general relativity, one of our two most fundamental theories about the universe. Whenever we find effects from general relativity in a new environment in the universe, it opens up interesting and novel ways to test our fundamental ideas about reality. The more extreme the environment, the better. And there are few environments more extreme than the violent neighborhood of an infant magnetar at the heart of the brightest supernovae in the universe. There may be other things around a magnetar that can make the accretion disk precess, including electromagnetic and Newtonian effects. But these fail to adequately explain the observational data as well as lens-Thirring precession, at least at our current levels of understanding of these systems. What is more, if general relativity really is the beating heart of this dying star, then these types of intriguing stellar explosions give us an unusually clear way to test our understanding of the cosmos at the highest level. Currently, this supernova is the only one we have seen chirp, and so there is a limit to how much we can probe our theories of fundamental astrophysics with it. But that won't be the case for long. The Vera C. Rubin Observatory just became operational, a behemoth 8-meter telescope which will observe the entire southern sky in the optical wavelengths hundreds of times over the next 10 years. Its legacy survey of space and time is expected to discover millions of supernovae over the next few years, likely including dozens of chirping, superluminous events. And when that happens, we will be watching.